mind-blowing AI-generated videos online.
Oh, yeah, absolutely. Some of them look incredible.
But it's always just a tiny glimpse, isn't it? Like 20 seconds of magic here from Sora, maybe 16 from MovieGen, 10 from Ray2.
8 from VO2,
Yeah.
I think, as of March 2025 for public access stuff.
Exactly. It feels like being teased with a movie trailer that, just never leads to the actual movie.
Right. You get the cool shot, but not the story.
And I'm guessing you, just like me, have thought, come on, I want to see a whole story unfold. That narrative thread that keeps you hooked, not just a pretty visual loop.
You've absolutely hit the nail on the head. These short clips show amazing potential, visually stunning stuff, but weaving those moments into something cohesive, something longer than a few seconds. That's been the real hurdle.
Which brings us perfectly to today's deep dive. We found this really fascinating research paper from CVPR 2025.
Which is kind of the Oscars for computer vision research, yeah. So a big deal.
Right. It's called 1-Minute Video Generation with Test Time Training. Now, hold on. Don't let that title make your eyes glaze over.
Yeah. Sounds a bit technical.
Our mission today is to really zoom in on the most valuable piece of tech in this paper, figure out how it works in a way anyone can grasp, and really understand how this could actually shake things up, in your work, maybe even just daily life. Because who wouldn't want AI that can tell a proper visual story?
Exactly.
Yeah.
And this paper tackles a fundamental bottleneck.
Yeah.
How do you get AI to make these long, coherent videos, complex stories even, without needing like a supercomputer the size of a small town?
Right.
The traditional transformer models, which are sort of the engine behind a lot of this AI magic, they just hit a brick wall when the sequence gets long.
How so?
Well, imagine trying to remember every single detail, every connection in a 1,000-page book, all at the same time. The processing power needed, it just explodes. It's this quadratic cost thing with self-attention.
Quadratic cost, meaning it gets way harder, way faster the longer the video.
Precisely. For a single 1-minute video, they calculated it needs to handle over 300,000 sort of visual tokens or building blocks. That makes generating the video about 11 times longer, and training the model takes 12 times longer. It's just incredibly slow and demanding.
Ouch. Sounds like a recipe for a very, very hot computer and a long wait.
Definitely.
And to really test if their approach could handle an actual story, they didn't just make pretty landscapes, did they? They went for Tom and Jerry.
Yeah, classic, right? Full of slapstick, those endless chases, scene after scene of cartoon mayhem. They figured if they could generate new minute-long Tom and Jerry episodes with all that dynamic action.
Then they really proved something about handling complex, long-form narratives.
Exactly. It wasn't about, making Tom look perfectly furry. It was about testing the AI's ability to keep that narrative thread going, capture all that dynamic motion over a whole minute. That's where current methods really struggle, keeping things coherent and engaging over time.
Okay, so before we get to their big idea, maybe touch quickly on why the other ways of trying this haven't quite worked for these longer, complex stories. The paper mentions things like RNN layers, Mamba, DeltaNet. They found efficient, but what's the catch?
Right, so those approaches, like RNNs, Mamba, DeltaNet, they are generally more efficient for long sequences in terms of raw computation. The problem is sort of like memory capacity.
Memory.
Yeah, they use what's called a hidden state. Think of it like an internal scratch pad to keep track of what's happened so far. But this scratch pad is a fixed size.
Okay.
Now, imagine trying to summarize a whole complex movie plot in just one short paragraph. You'd lose tons of detail, right? All the subtle connections, the setups and payoffs.
Yeah, you'd get the gist maybe, but not the richness.
Exactly. And trying to cram the essence of hundreds of thousands of those visual building blocks from a minute-long video into a relatively small fixed-size scratch pad.
Yeah.
It just can't hold on to all the long-range dependencies needed for a complex story. They might be okay for smooth motion within one scene, but linking multiple scenes, multiple plot points together coherently, that's the challenge.
It's like trying to build a skyscraper with only enough memory. Bricks for a small shed. Got it. Limited short-term memory for complex stuff.
Pretty much, which brings us to the star of the show. These test time training layers, or TTT layers.
Right, TTT. What are these things, and why are they such a big step forward? How are they different from that limited scratch pad?
Okay, this is where it gets really cool. Instead of that fixed-size memory bank that just gets overloaded, imagine the scratch pad itself is like a little learning machine, a mini expert inside the model that's constantly updating its understanding as it goes.
Oh. So the memory itself is intelligent?
Essentially, yes. That's the core idea of TTT layers. In the main version they tested, called TTT-MLP, the hidden state is actually a small two-layer neural network. So it's not just storing information, it's actively processing it, learning from it, refining its understanding on the fly.
That's wow. So not just taking notes, but like having a little research assistant inside who's actively listening, thinking, synthesizing, and updating their knowledge in real time. That's a neat twist.
It really is, and that leads right into the test time training part of the name. It means even while the AI is generating the video, at test time when it's actually drawing Tom chasing Jerry, these TTT layers are actively tweaking their own internal knowledge, their network weights.
Wait, so it learns while it's creating, not just from the initial training data.
Exactly. It's continuously learning and adapting based on the specific sequence it's working on right now. It's learning during the creative process itself.
That sounds incredibly powerful for keeping things consistent over a longer time. It's not just relying on past lessons, it's learning from the current job.
Precisely. And there's a clever mechanism inside called self-supervised learning. Basically, the TTT layer is constantly trying to, predict or reconstruct parts of the video sequence it's currently seeing.
How would you do that?
It forces the layer to really pay attention and understand the important relationships and patterns within the visuals, how things connect over time. The paper mentions these learned projections, TK, TK.
Okay. Jargon alert.
Yeah. Think of them like three special pairs of glasses the TTT layer uses. One pair helps it focus on what context to remember or pull from the sequence. Another highlights what's important right now. And the third helps it decide where to focus its processing power next. It's actively filtering and refining its attention.
So it's got its own internal director, making sure it focuses on the right bits to keep the story flowing. That's clever. And you mentioned flexibility. They can just plug these into existing AI models.
That's a huge plus, yeah. They demonstrated this by taking a pre-trained model, Cogvideo X5B, which was already decent at short clips, and they essentially just added these TTT layers as an upgrade.
Like adding a turbocharger to an existing engine?
Exactly. You don't have to rebuild the whole car. This means the tech could potentially be integrated into the video generators we already use, speeding up adoption.
Okay, so we have these smart, adaptable TTT layers, learning on the fly, easy to plug in. How does that actually let them make these full 1-minute videos without everything grinding to a halt or looking like nonsense?
They use a really smart hybrid approach. So for short segments, maybe like 3-second chunks of the video, they still use the standard local self-attention.
The thing that's good for details but bad for long sequences.
Right. Think of it as the AI focusing intensely on the immediate action within just that little 3-second window. Tom's specific reaction, Jerry's quick dodge.
Yeah.
Self-attention is great at those fine-grained local details within a short span. It's like focusing on one panel in a comic strip.
Okay, got it. Zooming in on the moment.
But then, crucially, layered on top of that, they have these global TTT layers that process the entire 1-minute sequence. These are the layers responsible for maintaining the long-term coherence, making sure the story flows logically from start to finish, that actions have consequences later on. It's like reading the individual comic panels while also keeping the overall plot of the whole comic book in mind.
That analogy really works. Local attention for the details in the scene, global TTT for the big picture story arc.
You got it. And they introduce these TTT layers carefully, using something called a gating mechanism. It involves some learnable parameters, alpha and beta.
Sounds technical again.
Think of it like a dimmer switch. Since the original Cogvideo X model wasn't trained with TTT layers, you can't just suddenly switch them on full blast. It would mess everything up. This gating mechanism lets them sort of gradually fade the TTT layers in during training.
Gently introducing the new ingredient so it doesn't overpower the recipe.
Exactly. It lets the TTT layers start contributing without totally disrupting what the model already learned. A smooth transition.
Makes sense. Don't shock the system. And they also mentioned bidirectional processing, looking forwards and backwards.
Yes, that's important for the type of model they're using, a diffusion transformer. These models often work by looking at the whole sequence context, past and future frames, to help generate the current frame. So having the TTT layers process the sequence in both the forward and reverse directions lets them capture a much richer understanding of the overall context.
Like reading a story, then reading it backwards to catch all the foreshadowing.
Something like that. It helps ensure consistency across the whole minute.
Okay, got it. So back to Tom and Jerry. Why was that such a good test, and what did the results actually show? Did the TTT magic work?
Like we touched on, Tom and Jerry is perfect because it's all about complex, multi-scene stories with tons of action. It really pushes the long context problem rather than just asking, does it look real?
Hmm.
And can it handle Tom setting a trap in scene 1, Jerry dodging it in scene 2, and Tom getting hit by his own trap in scene 3, all coherently over a minute?
Less about perfect fur, more about cartoon physics, cause and effect over time.
Precisely. And the results.
Mm.
Pretty darn impressive. They compare their TTT MLP approach against strong competitors, Mamba 2, gated DeltaNet, even just using standard attention, but only looking at a small sliding window.
Mm.
And in human evaluations, actual people watching and rating the videos, TTT MLP came out significantly ahead. They used the ELO rating system, like for chess players.
Oh, yeah.
TTT MLP scored a whopping 34 ELO points higher than the next best baseline for the 1-minute generation. That's a really substantial difference, especially in things like temporal consistency, making sure things stay coherent over time, and motion smoothness. It directly tackles that desire we have for AI videos that actually tell a sensible story.
Wow, 34 ELO points. That sounds like a knockout, even if I don't fully grasp the scale. It really shows this TTT thing is effective for longer stuff. And they could feed it different kinds of prompts, right? Like summaries or detailed plots.
Yeah, they tried different formats, simple summaries, more detailed plot outlines, and even super detailed frame-by-frame storyboards. Interestingly, the video model itself always worked best with the most detailed storyboard format.
So you had to write a detailed storyboard?
Not necessarily. They cleverly used another AI, a large language model, to automatically take the simpler prompts like your summary and expand them into that detailed storyboard format 3 they called it, that the video model needed.
Ah, so AI helping AI. You give it the basic idea, and the language model writes the detailed script for the video model. That sounds pretty user-friendly, actually.
It is, yeah. Makes it more accessible.
Okay, now for us non-coders, can we peek under the hood a bit? How did they actually make this work without, melting the computer? Maybe keep it light, some humorous analogies?
Absolutely. Let's try. So even with TTT being more efficient for long stuff, you still can't just cram that whole minute-long sequence, all 300K plus tokens, into the AI at once. It's like trying to drink from a fire hose, right?
Yeah.
Too much.
Overload.
So to manage this and speed things up, they use something called an interloop mini-batch. Okay, imagine you have to read a super long, complex instruction manual. Instead of reading it cover to cover slowly, you maybe speed read each chapter in chunks, just grabbing the key points quickly before moving to the next chunk, but making sure you still get the overall flow.
Okay. So processing the video in faster, smaller bites, but still understanding the whole story.
Kind of like that. Processing manageable segments quickly to keep the calculations from bogging down, but the TTT layers help maintain that long-term understanding across the chunks.
Eating the elephant one bite at a time, but making sure it still connects together. I like it. What else?
Well, those TTT calculations, especially with a little neural network inside the hidden state constantly learning, can still be pretty demanding for the GPU, the graphics card, the AI's powerhouse brain.
Right. Got to keep the brain cool.
So they use a clever trick called on-chip tensor parallel. Now picture the GPU having lots of tiny specialized processing units. They're actually called streaming multiprocessors, or SMs. Think of them like little brain cells, or maybe chefs in a very efficient kitchen.
Okay, chefs in the GPU kitchen.
Right. This tensor parallel technique basically divides up the really heavy TTT cooking tasks among these different chefs. Each chef, each SM, gets a specific part of the recipe, a piece of the complex calculation.
So they're working in parallel. Teamwork.
Exactly. Teamwork among the GPU brain cells. No single chef gets overwhelmed with too much work. The whole meal, the video frame, gets prepared much faster, and you avoid kitchen disasters like running out of counter space, which is like running out of memory on the chip.
Haha.
A well-organized GPU kitchen with specialized chefs avoiding memory meltdowns.
Love it.
That actually makes sense. Now, even with Tom and Jerry dancing smoothly thanks to the GPU chefs, the researchers were honest about limitations, weren't they? Yes, absolutely. And that's important for keeping our expectations grounded. While TTT MLP was the champ for the full 1-minute videos, it wasn't actually the best performer for shorter, say, 18-second videos. In those shorter sprints, gated DeltaNet, one of the other methods, actually edged it out slightly.
Interesting. So TTT is maybe overkill for shorter stuff?
It suggests that, yeah, different tools for different jobs.
Yeah.
You don't need the super long-term memory feature if the story is really short, like using a huge truck just to move one small box.
A marathon runner isn't always the best sprinter. Makes sense. Any other downsides?
Well, currently, TTT-MLP is still a bit slower, both for generating the video, inference, and for training the model, compared to some alternatives like gated DeltaNet or Mamba 2.
Ah, so there's a speed trade-off.
Right now, yes. They've made strides in efficiency with things like that tensor parallel trick, but it's still an area that they're actively working on. Think of it as a powerful new engine that's maybe not quite perfectly tuned for top speed just yet, still under development.
Okay, so longer, more coherent video, but takes a bit more processing time for now. Fair enough. What about the actual look of the videos? Were they perfect?
They acknowledge there are still some visual artifacts, things like occasional flickering between frames, maybe some slight temporal inconsistencies the TTT didn't quite smooth out, motion that sometimes looks a bit unnatural, or minor aesthetic issues with lighting or color.
So not quite Pixar level yet.
Not quite. They think a fair bit of this might actually stem from the limitations of the underlying pre-trained model they started with, the Cogvideo X. It's like having a brilliant storyteller who's maybe working with slightly limited animation software. The core storytelling ability is improved by TTT, but the final polish depends on the base model too.
Okay, so the TTT improves the story coherence, but visual quality also depends on the foundation it's built on. Understandable. So looking ahead, what are the researchers excited about? What's next for TTT?
Oh, they see a ton of potential. A big focus is just making it faster and more efficient. Optimizing the code, finding better ways to use the GPU power, maybe new algorithmic tricks.
Getting that engine tuned for speed.
Exactly. They're also exploring even better ways to integrate TTT layers into models. That gating mechanism was one way, but maybe there are smoother, more effective ways to blend this long-term memory capability with existing architectures.
So tighter integration, faster speeds.
And perhaps the most exciting direction.
Yeah.
They talk about using even larger, more complex neural networks as the TTT hidden state itself.
Like a bigger brain inside the memory?
Yeah, they even float the idea of putting a whole transformer model inside the TTT layer.
Whoa, a transformer within a transformer layer, that's getting meta.
Right. But it could potentially unlock much more sophisticated long-term reasoning and memory, paving the way for generating significantly longer and more intricate video narratives. Imagine going from 1-minute cartoons to maybe AI-generated short films.
That's a genuinely thrilling thought. The potential for complex, engaging visual storytelling. It could really be transformative. So, okay, wrapping up this deep dive, what's a key takeaway for our listener? The person who doesn't know tensor parallel from TensorFlow, what's the valuable nugget here?
I think the most valuable thing is that TTT layers represent a really significant step forward, a potential game changer for making longer, more complex videos that actually make sense. By giving AI a more dynamic, adaptive way to handle long visual sequences, it starts to break down those old barriers. It's not just longer video, it's longer video with coherence and story.
And even without the technical nuts and bolts, the potential impact on work, on daily life. It could be huge, right? Imagine more seamless visual explanations, richer educational stuff, more immersive entertainment, totally new creative tools.
Exactly. Imagine creating a quick animated explainer for a work project in minutes, or visualizing data unfolding over time, or just telling your own stories visually in a much more substantial way than before.
It could really democratize video creation even further.
That's the hope. It's not just cool tech. It could fundamentally change how we communicate and create visually.
So final thought for everyone listening. Now that generating a coherent minute of video is becoming possible, what kind of longer, more complex visual stories do you see emerging? How might that change how we learn, how we work, how we share ideas, how we entertain ourselves? It's definitely something to mull over, isn't it? What happens when these limits keep falling away?
It's going to be fascinating to watch.
Absolutely. And you can be sure we'll keep diving deep into advancements like this right here. Thanks for tuning in.